Hi, in this video we're going to learn a new rule for combining functions to find derivatives. So before we get to the rule, we're actually going to look at some problems and make sure we're clear about how functions are combined. Alright, so the first function that I've got here says y equals sine of x squared. If you read that correctly, sine of x squared. The second function has an x squared and a sine function, but it's a little different. Second function, if you read it, it would be read y equals x squared times sine of x. The key thing here is that these functions both involve an x squared function and they both involve a sine function, but they're combined in different ways. In the first one, I have an x squared function that is inside a sine function. So in that one, the way those two functions are combined, the x squared function and the sine function, what we really have here is composition, a function inside another function, f of g of x, where the g of x function, the inside function, would be the x squared function, and the f function, what it's put into, would be the sine function. On the second example, we've got an x squared function and a sine of x function, but those two functions are times each other, x squared times sine of x. So for that one, we've got an f of x times g of x function. Alright, so we already know some derivative rules for finding one of these derivatives, but not the other one. So if you've been working on all the stuff that we were supposed to be working on so far, you should say, oh, I know how to do products of functions, derivatives of products of functions. I'm going to use product rule for that. So we have a product rule for derivatives of products of functions. But we don't yet have a rule for finding derivatives of functions inside other functions. So we're going to need a new rule for something like that, functions inside other functions. I'm going to go ahead and just write down the derivative of the one using product rule, just in case you want to practice. Pause the video, write it down, and check to see if you got the right thing. Okay, so I went ahead and wrote down the derivative for the second example here using product rule that we already knew how to do before. So hopefully you practiced that, you double checked, and that's what you got. But the real point of this video is being able to think about finding derivatives of functions like this, where we have a function inside another function. So that rule is called chain rule. I'm going to scroll up here and write down chain rule, and then we'll use chain rule to find the derivative of that function, where we've got a function inside another function. Okay, so the chain rule can be written a lot of different ways. So the way I have it written down here, I have the derivative with respect to x of this f of g of x. So the key thing here is how these two functions are related to each other. I have an inside function here, which would be the g of x function, and that function is inside the f of x function, and that would be an outside function, or inner and outer. I sometimes say inside and outside, or inner and outer functions. Okay, so I'm going to write down the chain rule here, and we're going to practice using it. I'm going to point you towards some resources that help you understand why this rule is true, a proof of this rule, and also some other ways to think about this rule. But for this video, we're just going to practice memorizing chain rule and then applying it to a couple of easy example problems. Alright, so what chain rule says is that the derivative of f of g of x is f prime, so that's a derivative of g of x, times g prime of x. And you can memorize this rule in a lot of different ways, using f primes and g primes, or u's and v's, or inners and outers, or all kinds of other notation as well. So however you think about it, it's really the same rule. This is how I usually write it, and I'm going to talk about it in this video. So what this first part here says is we're taking the f prime, so that's the derivative of the outer function, and notice that the inside part there, the g of x that's inside there, is just the inside function left alone. Derivative of the outer function, and on that part we're leaving the inside alone. On that part. And then times, and then after the multiplication we've got g prime of x. So that's the derivative of the inner function, or the inside function. So the derivative of the outer function, leave the inside alone, times the derivative of the inner function. Okay, so I'm going to erase some of this writing I had up here for the y equals sine of x squared. I'm going to make some space so that we can use chain rule to find that derivative. Okay, so we're going to work on this problem here, y equals sine of x squared, and we already talked about that on that problem I have a function inside another function. The outside function here is the sine function, and then the x squared function is inside that function. So when I think about the chain rule here, whether you call them f and g or whatever you call them, you've got an outer function and an inner function. All right, so just like when I did some of these other rules, I'm going to go ahead and kind of set up a structure for myself and then fill in the pieces. So this is my y. My derivative is going to be dy dx or y prime, some correct notation for derivative. And then I'm going to go ahead and set up some parentheses here. So chain rule says derivative of the outside, leave the inside alone. And then times the derivative of the inside. Okay, so now I'm just going to go back and fill in those pieces here. All right, so the outside function is the sine function. So I want to think to myself, what is the derivative of the sine function? And you should quickly say the derivative of sine is cosine. And so we're going to say the derivative of the outside function would be cosine. Derivative of sine is cosine. Leave the inside alone. Leave the inside alone. So I just took the derivative of the sine part of the problem here. Leave the inside alone. And then I'm going to take that whole thing times the derivative of the inside function. So I'm going back to my original function and looking at what my inside function was. The derivative of that inside function is what goes in this last parentheses here. So this will be the derivative of x squared, which is 2x. All right, so there's my derivative. If I want to tidy that up, I could write that as 2x times cosine of x squared. And that would be a cleaner way to write my derivative. All right, so chain rule. Derivative of the outside, leave the inside alone, times the derivative of the inside. All right, we're going to look at a couple more examples here, quick examples, and then some harder examples in the next couple videos. So, all right, so chain rules there at the top. We've got an example here at the bottom where I have a function inside another function. If I read this, I have y equals e to the x cubed. So for this one, my x cubed function is inside the exponential function, e to a power of whatever. So that exponential function, e to a variable power, is the outer function. All right, so remember chain rule? I'm going to scroll up so you can't look at it anymore. Make sure you have it written down or you remember it. Okay, so here we go. So we're going to apply that to this function. All right, so when I take this derivative, I'm going to say derivative is, I'm going to use some structure so I don't get lost in the problem. Use some labels here. Derivative of the outside, leave the inside alone. Then times the derivative of what's inside. Okay, so then just fill in. All right, so the outer function is the exponential function. Derivative of e to the variable power, well, derivative of e to the x is e to the x. So here, derivative of e to a power is just e to that power. If the power is not just x, though, then there's some chain rule going on. So like we have here, the derivative of exponential function is itself, that's the derivative of the outside part, but then times the derivative of what's inside. So this would be times the derivative of the x cubed function. So 3x squared. Okay, and then I could just write that as 3x squared times e to the x cubed. Nice little derivative there. Okay, we're going to look at one other problem here that is kind of so easy it's hard. Students often miss this kind of problem when they shouldn't, and this will cause you a lot of grief if you can't get this kind of problem right. So This one is a lot like the previous problem, except it's actually simpler, but sometimes when students should only see an extra constant inside there, they don't really seem to think about it as chain rule. But if you have more than just e to the x, derivative of e to the x is itself. But if I have a derivative of e to the anything other than just the variable x there, any extra pluses, minuses, coefficients, anything extra in there, then there's really a chain rule going on in the problem. So that's what we have here. Our inner function is 4x, and outer function is exponential function. So our derivative, dy dx, is, I'm going to label these again one more time here, derivative of the outside, leave the inside alone, times the derivative of what's inside. Okay, so derivative of e to a variable power is, just that. Derivative of e to the x is e to the x. So derivative of exponential function is that exponential function. But again, if you have anything other than just x in that exponent of that exponential function, there's really chain rule going on, and so you need to not forget that. So the next part that I need here is the derivative of that 4x. So derivative of 4x is just 4. So my answer is 4e to the 4x. So sometimes students memorize a rule about derivative of e to the constant times x, and they've got the same constant out front, which is okay, but really you should understand that that's really chain rule going on here, that extra 4 out front really comes from chain rule and finding the derivative of that inside function. Okay, so there's some harder examples of chain rule in the next couple videos, so watch those too.